Okay, good evening to all, and welcome to the another session of the NPTEL course Heat Transfer. So this is our week six section. So today we will be discussing about the topics that were covered in the week six. Maybe some of the practice questions related to the topics covered in week six, which is basically the flow over a flat plate and just introduction to the internal flows. So in week six, for a flow over a flat plate, the Blasius equations were derived using similarity solutions, and then the Nusselt number derivation, uh, then friction factor derivation, all were done. Then internal flows means flow through a duct or a pipe were also discussed. Means force convection through an internal flow. These were the major contents in the week six. So today we will discuss some of the practice question related to these topics. So let's get started with the first question. So we have an air which is at 27 degrees Celsius is flowing with a free stream velocity of 10 meter per second. Yeah, is used to cool electronic device mounted on a printed circuit board. So each device is 4 mm into 4 mm, dissipates 40 milliwatt, which is to be removed from the top surface. A turbulator is located at the leading edge of the board, causing the boundary layer to be turbulent from the initial stage itself. Estimate the surface temperature of the fourth device located 115 mm from the leading edge of the thermophysical properties are also given. So you can just start doing this. So I hope the question is clear. If you have any doubt, you can ask. So here the flow is full completely turbulent from the leading edge itself. So you have to use the Nusselt number equations, Nusselt number formula for turbulent flows or a flat plate. That's the only thing you have to take care in this question. Otherwise, we have done a multiple similar kind of questions in the previous session. Anyone got the answer? Okay, in this question, the each device is emitting a heat of around 40 milliwatt, and we are assuming that the device surface is isothermal. It's an assumption. Okay, so it's like we can assume this. So our area of interest is like this fourth plate or the fourth component. So it's like a uh, means flow over a flow over a flat plate with constant surface temperature. Like our area of interest is fourth, but the flow happens from here to here. So what is the approach we have to do? So how we will get the surface temperature? So what is the first step? We know how much is the amount of heat that to be dissipated, like right, that is 40 milliwatt, and we know the surface we know the free stream temperature of air. So we are asked to find out Ts. Okay, so what is the quantity we need to uh, find out in order to estimate this?
We need to find convection coefficient first.
Yeah, we have to find out the convection heat transfer coefficient. So for that we have to use the
Equation for the turbulent flow.
yeah. So do you know that is nu x at any location x is equal to
So that
points?
I think that I was searching 0.0296. Reynolds number is to power 0.8. And
Is this right? Yeah,
yeah, potential number
yeah,
1 by 3.
yeah. So just substitute in this value, you will get the answer. First, you need to find out what is Reynolds number at x. Okay, that is u infinity x divided by mu. That is 10 into x is 15 mm. So 15 into 10 raised to minus 3 divided by the what is the mu? That is 17.4 into 10 raised to minus 6. What is the Reynolds number?
Eight 8,620.
Yeah. Okay. So now we have to, but Prandtl number is already given, that is 0.705. So can you please find out what is Nusselt number at x is equal to 0.015 meter is, which is 0.026 into 8260 raised to 4 by 5 into 0.705 raised to 1 by 2. I think you will get around 37.1 or something, um, closer to this.
37.1, sir.
Yeah. So next we have to find out the heat transfer coefficient at that location, which is k pi l into nu x, which is equal to k is given how much? point 0296. Sorry, yeah, can take this as 0.027 divided by 0.015 into 37.1. What is this answer?
or 66.8.
Yeah, 66.8 watt per meter square Kelvin. Now you got everything which like cube, the heat balance, like it's we have to estimate what is the heat flux, that is Q by area of cross section into H that at that location, or Hx into uh, Ts minus T infinity. This Q is known 40 milliwatt. Area is known, that is 4 into 4 into it's 4 mm into 4 mm. Right? Yeah, into 10 raised to minus 6. Hx we already know. This is 66.84. T infinity we know how much. It's 27 degrees Celsius. So what is Ts?
So is it 64.4?
Yeah, it's close to 66.4. Sorry, 64.4. Okay. So I think this is a question similar that we have done in the previous week also. The only thing is now it's a turbulent. So and the previous questions we are only dealing with laminar. Now the entire uh, board is turbulent by means, as I said in the previous classes also, it made turbulent by using a turbulator, okay, in the leading edge. So unless it is not specified, you have to check what is the you have to go with the conventional way, that we have to check what is the Reynolds number, like that. If it is critical, sorry, laminar or turbulent, like that you have to check.
Sir, I want to that I have a query in question number one.
I think it's maybe with this Reynolds number.
No, that
Then
whenever we are using this equation 0.0296, whether for turbulent or for laminar flow, so
hmm.
potential number range is also there that is mentioned.
Yeah, it's this is between 0.6 to 6, I think. I don't remember, 6 or 6,
60,
60,
60, sir,
60.
60.
Yeah, yes.
Uh, so we never emphasize on potential number, and we always assume that whatever potential number is given, that is within that range. I think what is in the most of the problems we are never emphasizing on potential number along with Reynolds.
No, the Prandtl number here is 0.7, right? So it falls inside that region.
Because when you have written this equation, Nusselt number is equal to 0.0296, Reynolds 4 raised to power 5,
Yeah.
Prandtl 1 by 3. So we are never writing that Prandtl number should be within zero point 0.6 or 60. We never write it in any of the books, in the books also even. We always presume that in the statement, whatever is given, that is within the limit.
No,
This
no,
is what I.
I didn't write because the Prandtl number is zero point 0.7. That's why. Means
Okay,
you should check the
okay,
Prandtl number is not within this range. Then you have to go to other equations. As it
okay.
is, Prandtl number is zero point 0.7. Yeah, it's always good to write this limit. Okay. So most of the cases we are dealing with Prandtl number in this range. Okay, like air. So the low Prandtl number goes to like liquid metals and all. So there we have to uh, use other equations considering that lower Prandtl number. And also I think in one equation is there. Uh, I don't remember. So which is true for any Prandtl number ranges. So you can check in the web. Uh, I don't remember it. I don't remember the equation, but there is one equation. It's like for liquid metals where the Prandtl number is very less, there is another equation. Like that, you have to check which range the Prandtl number falls. If you are following Incorpora, it's clearly written all these things. So if you have further queries, you can refer back to that text. Which are Prandtl number you have to check.
Okay, sir.
So we'll move to the next question. What is the minimum free stream velocity if the surface temperature of the fork device is not to exceed 80 degrees Celsius? So now the surface temperature is given. So we have to find out with the same heat flux. We have to find out what is the minimum air velocity we should maintain in order to not to exceed 80 degrees Celsius. It's like the opposite or the reverse of what we have did in this question. So I think we will be able to solve it. So I will wait for 2 minutes. Just do the reverse of what we have done here. Okay. So you will I we will get the Reynolds number. From the Reynolds number, you can easily find out what is the minimum velocity or the velocity. You got the answer. Like the surface temperature is 80 degrees Celsius. What is Hx, which is Q by A Ts minus T infinity. This is 40 into 10 raised to minus 3, 4 into 4 into 10 raised to minus 6, 80 minus 27. So what is the heat transfer coefficient that should be maintained? Did you got this?
Why we are calculating different? We should use the previous value of h here, isn't it?
No, no, because the velocity is changing, right? So it depends on Reynolds number.
Okay, okay.
The questions are the minimum free stream velocity that we should maintain so that the surface temperature of the device will not exceed 80 degrees Celsius. So here the free velocity is changing. Velocity is changing means Nusselt number will change. So you will get around 47.17 watt per meter square Kelvin. Are you getting
Yes,
this?
47.2. Yes, sir.
Yeah, okay. So this you should put it in the Nusselt number equation, that is Hx is equal to K by L uh, times 0.0296 into Reynolds number raised to 4 by 5, Prandtl number raised to 1 by 3. So this you know, that is 47.17. K is how much? 0.027 into 15 into 10 raised to minus 3, 0.0296. The Reynolds number is the quantity we need to find out. Prandtl number we know, it's already given. Okay. So we need to find out what is the Reynolds number. So we will get around 77,654.8, almost close to this answer. Okay. Are you getting this?
I have not calculated, sir.
Yeah, okay. Then you can calculate that later. So it will be, you'll get around this value. So then you can use U infinity x or L divided by mu. So what is U infinity? That is 7654.8 into 17.4 into 10 raised to minus 6 divided by 15 into 10 raised to minus 3. Can you please calculate this answer?
Sir, 8.9.
Yeah. So the velocity is around 8.9. So this is the minimum velocity we should maintain in order to we should in order to get the surface temperature. So in order to restrict the surface temperature above 80 degrees Celsius. Okay. So if we go below this velocity, the Heat-Transfer coefficient will reduce. So it will increase the surface temperature.
But sir, why we are using here the local that value of Hx? We should use here the average.
Because this is not the plate. On the plate, we are mounting these devices. Okay. So this device is independent. This is not, it's like this, we are having a plate and the heat transfer coefficient is varying along the plate. So this local heat transfer coefficient only matters for this fourth device. I hope you got this. It's not the average because we are not concerned about what is the what should be the average heat transfer coefficient. Average heat transfer coefficient means from x to this 15 mm. That is not our concern. Our concern is only the heat transfer from this small chip or any device which is located at 15 mm from the leading edge. I hope it is clear.
Okay, sir.
So you should analyze the question also. What is our point of interest? Like that, we should check. Okay, we should then only we should start proceeding with the solution. So next is another question. So we have a 100 electrical components, each dissipating 25 watts, are attached to one surface of a square copper plate, and all the dissipated heat is transferred to water in a parallel flow over the opposite surface. So a pro-turbulence at the leading edge acts to trip the boundary layer, and the plate itself may be assumed to be isothermal. The water velocity and temperatures are given. The thermophysical properties are also given. So we should find out what is the temperature of the copper plate. Okay, so I hope you understood the question. Okay, so we have a surface onto which 100 electrical components are attached. So each dissipating around to 25 watts, that is Q is equal to 25 into 100, which is 2500 watts. So this is the heat that should be dissipated from the entire plate. So, and we have on one surface, we have the this components which is dissipating heat, and this which is generating heat, and this heat is dissipated to the water which is flowing at the opposite side. Okay, so I hope you can visualize the situation. So this is the plate, and let's assume that at the bottom we have the uh, components, and at the top water is flowing. It's like a flow over a flat plate. Okay, and we can assume that the device surface is isothermal. So with that, we can assume that the Nx, that is heat transfer coefficient, sorry, Nusselt number is equal to 0.0296, Reynolds number x raised to 4 by 5, Prandtl number raised to 1 by 3. So here we should take the local or average heat transfer coefficient or average Nusselt number. We should take average.
Average.
Yeah, here we should take the average Nusselt number. So nu bar is equal to, so you have to What is
Excuse me, sir. That first we will be calculating the Reynolds number.
because it's already given. Na? So the a pro turbulence at the leading edge acts to trip the boundary layer.
Oh, so it is fully turbulent.
Yeah. So can you find the expression for this? Means like what is the average trans coefficient? Is from
Sir,
this
actually,
expression.
if I calculate the Reynolds number, we are
Hmm.
using 0.2 meter length,
Okay.
then it is coming out to be laminar.
Okay, that's fine because it's like it depends on the fluid. Means the Reynolds number depends on U infinity L and U. Like it doesn't consider whether we have tripped the boundary layer or not.
Okay.
That's why it is coming like this. But in the question, it is clearly written. We have to take the turbulent. We have to assume that the flow is turbulent.
Yes, sir.
Yeah. So can you find out what is the average Nusselt number? Okay, so you will get the if you do this calculation, you will get around 0.039 Reynolds number raised to 4 by 5, Prandtl number raised to 1 by 3. Okay, so I think you already found out what is the Reynolds number at L. That is, what is the Reynolds number? Can you please find out? Say,
4.2 into 10 to the power 5.
yeah. So please put this Reynolds number value and find out what is the average heat transfer coefficient. So, yes. I think the Prandtl number is 5. Yes. So the K is already given. K is point 0.62 and L is 0.2. That is the heat transfer coefficient.
Sir, 622 9.4.
How much?
622 9.4.
6.
229.4.
So now you got the average heat transfer coefficient. So just substitute this. So Q is given, that is 2500 watts. So what is the total area? Zero point 0.2 into zero point 0.2. H we already found out. So what we need to find out is Ts. So T infinity is already given. How much? 17. Okay. What is Ts?
So 27 degrees Celsius.
Yeah.
Sir, but you have earlier written that average heat transfer coefficient is to be found by integration. So I was putting that x raised to power minus 1 by 5 there, then we will be integrating, isn't it? Or we will be directly putting Reynolds number here.
Which one? Which one?
Like you have written this HL is equal to 1 by x 0 to L hx dx. We have to integrate.
Hmm.
So then hx we will be putting equal to k by L 0.00296.
Ah, yeah,
Don't
that you have to
don't
put.
we will
Yes.
be integrating it.
Yes, yes.
So so that step we, so it means there is that HL can be calculated by two ways. Like
How?
you have put directly Reynolds number here, but you have not integrated.
So this coefficient you check, it's changing, right?
Yeah.
Coefficient is not same. After integration, you will get anyway end up with 4 by 5.
Yes.
Yeah. So this type of question we already did in the previous classes, right? How to calculate the average heat transfer coefficient.
No,
Okay.
sir. It means when we are using the direct equation. So then direct equation we have got after integration. It means no.
No, this which equation?
This Nusselt number
Ah,
0.037.
you check if you after integration you are getting this.
Okay.
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 Okay. Let's move on to the next question. So, okay, this is also a continuation from the previous question. So, if each component has a plate contact surface area of 1 centimeter square, and the contact resistance is given 2 into 10 raised to minus 4 Kelvin meter square per watt, what is the component temperature? Now, we can neglect the temperature variation across the thickness of the copper plate.
So, sir, rate of heat transfer is equal to the drop in temperature divided by resistance, both convection as well as conductive.
Yeah, because it's not required. We already know what is the TS. Okay. And we have a contact resistance between the surface TS. TS we already found out from the previous question, that is from 27 degrees Celsius. And there is a contact resistance between the plate and the uh, and this component. It may be because of the thermal paste or something, it may be attaching, that is a contact resistance. And we are asked to find out what is the temperature of the component, Tc. Okay. And we are asked to, we can neglect the temperature variation across the thickness of the plate. That's also given. So it's like Q is equal to, that is the heat flux that is going, is equal to Ts minus Tc, sorry, Tc minus Ts divided by the contact resistance. Okay, this is how we should solve. So what is Tc? That is what we have to find out. So Q we already know, that is 25. Then Ts already found out 27. RTC is given, that is 2 into 10 raised to minus 4. Then area of contact surface area is given, that is 1 centimeter square. So it's like 25 is equal to Tc minus Ts is 27, 2 into 10 raised to minus 4 divided by contact surface area, that is 1 into its centimeter square. So we have to convert to meter square. So can you please find out what is Tc?
77.
Yeah, will be around 77 degrees Celsius. Okay, let's move on to the next question. So we have a airflow which is over a heated flat plate at a velocity of 50 meters per second. The local skin friction coefficient at a point on the plate is given, that is 0.004. We have to estimate the local heat transfer coefficient at this point. A similar question we did in the last week, so I hope will be able to solve this. So how to solve this? How to solve this question?
Sir, we did it with shear force last time.
Yeah, means modified Reynolds analogy you have to use. So we are given u is equal to how much? 50 meter per second, and the local skin friction coefficient is given 0.004. We have to find out what is hx, a local heat transfer. So we have the modified Reynolds analogy, which is equal to, am I right? So we have to Cfx is given. The Prandtl number you have to find out, that is mu Cp by k. That is mu is given Cp. Can you please find out what is the Prandtl number? What is the Prandtl number?
0.66.
Yeah. So standard number last I already defined what is standard number. That is, I hope you remember. What is the standard number?
So Reynolds into Prandtl number.
No, no, that's not standard number. That is Reynolds by a Nusselt number divided by Reynolds number into Prandtl number. Reynolds number into Prandtl number is Beckley number.
Okay.
But that I reduced to this HX form. Do you remember what is that form? So you can
So
refer back to the
that was
H.
CF by 2 equal to H by rho U infinity Cp Prandtl 2 by 3. Is it valid?
Yeah, the standard number, that is Nu divided by Reynolds number, Prandtl number. So if you simplify this, you will get H divided by rho Cp U infinity. This derivation I already did in the last class. You can refer back. Okay. So just directly put this value here, Hx. That is what we need to find out, that the local heat transfer coefficient, rho Cp U infinity, Prandtl number raised to 2 by 3, Cfx divided by 2. So Hx rho is given 0.88, Cp U infinity is 50, Prandtl number is 0.662 by 3, CFX 0.004 by 2. Can you please calculate what is HX?
116. 116.
No, actually, I was just calculating. So, what is the answer you're getting? 116.
I'm getting 116, sir.
Okay. Okay, fine. Because I'm getting one order less. Let me check where. Oh, okay, okay. Uh, okay, I used the velocity as 50 meter per second. Means I use velocity as 5 meter per second. Okay, then it's right. Right, it's one order less. So I'm getting 11.6. You are getting 116, right?
Yes, sir.
116. Then what is any decimal points?
Point 4, sir.
Point 4. So that was my mistake. Then yes, I calculated with 5 meter per second. That's okay. So I hope this question was clear because we have already It's just a direct application of Reynolds analogy, modified Reynolds analogy. Now we have another question. We consider an air at 2 meter per second and a temperature 300 Kelvin in a parallel flow over isothermal flat plate of 1 meter and temperature 350 Kelvin. Calculate the local convection coefficient at the trailing edge without unheated starting length. I think this is a normal question only. So we have a flat plate. Uh, which is isothermal. The temperature is maintained at 350 Kelvin. Okay, and we have a flow of air at 2 meter per second with 300 Kelvin temperature. We have to find out the local convection coefficient and the trailing edge, which means that x is equal to 1 meter. So can you please calculate and say, because I will wait because we have done a n number of questions similar to this. So
But sir, what is the meaning of without unheated starting length?
which means the entire plate is heated from the starting length, starting itself. From x is equal to 0 onwards, it is heated. So this is a normal question. So we have a flat plate which is at surface temperature of 350 Kelvin, and there is a flow of air at 300 Kelvin and 2 meter per second. So we are asked to find out what is the uh, heat transfer coefficient at trailing edge. So what is the expression for Nusselt number? The local. So any x is equal to. So first we have to find out what is the Reynolds number, because like in the previous question, there is no mention that it is from initial onwards it is turbulent. So we have to check what is the Reynolds number at x is equal to L. It is U infinity L divided by mu. That is 2 into 1 divided by 18.4 into 10 raised to minus 6. What is the Reynolds number?
1.1 into 10 to the power 5.
Okay. So this is in laminar regime. So we have to use the laminar flow equation, that is nu x is equal to 0.332 Reynolds number at x raised to 1 by 2, Prandtl number raised to 1 by 3. Okay, so can you please find out what is the Reynolds number at x is equal to L is equal to 1 meter?
Sir, won't this equation be 0.664?
0.664 is for average Nusselt number. Right? This is I am taking local. Because in the question it is asked the local convection coefficient at the trailing edge. What is the Nusselt number value? Or we can directly find out what is x, that is k by L.
So 98.
98.
Yeah.
Okay. Can you, what is the hx? K is 0.0282.
2.8.
Yeah, 2.76 watt. Okay. So this is a normal question that we have already did. So now comes the another a type of question where we have a unheated starting length. Unheated starting length in the sense, if this is a plate, okay, just yeah, if this is a plate, the flow is happening, and the thermal boundary layer grows. Okay, sorry, the hydrodynamic boundary layer is growing from the leading edge itself, but there from this point onwards only the heat transfer happens. Okay, it's like say at a distance eta from the leading edge only the surface temperature is different, is T infinity. The surface temperature is greater than T infinity. Up to this, for a certain distance, eta is equal eta, the surface temperature is equal to infinity. So whether the thermal boundary layer starts from here or here.
So the thermal boundary layer will start from where the heating will start.
Yeah. So we have a thermal boundary layer like this. So this is the case of a flat plate with a parallel flow with an unheated starting level. Okay. So I just introduced this question because there is a concept like this. So just to introduce that there is a concept like this. So in the textbook, we will get the direct equation, that is nu x is equal to uh, nu nux when the eta is equal to 0, means when there is no unheated starting length in divide by 1 minus eta by x raised to 3 by 4 to 1 by 3. So this is the expression for a Nusselt number when there is no, sorry, when there is a unheated starting length. So can you please, according to this question, what is the eta here?
1 meter.
Yeah, it is 1 meter. Okay, and x here means because at the trailing edge. So what is x here? X is equal to L, which is equal to how much?
It is 1 meter again, I think.
Okay,
There is problem in the question.
yeah, you can take the length as 2 meter in this question. The same condition with the 1 meter starting length and length of the plate as 2 meter. Maybe I missed that part to type. Okay, yeah, now it's fine. So x is equal to L is equal to 2 meter. So what we need to find out is at x is equal to L. So first we have to find out what is the Nusselt number at x is equal to L when there is no unheated starting length. Okay, divided by 1 minus epsilon by x. This in this case it is 1 by 2.5, 3 by 4, 1 by 3. So first find out what is nu x is equal to L, means the normal flat plate case. For that you have to find out what the Reynolds number. Find out the Reynolds number. It's just multiply the this one by 2 because the length we are multiplying by 2. So the Reynolds number will be 2 times this value. So it is 2.2 something into 10 raised to 5. Okay. So still it is a laminar region. So nu x is equal to L when there is no unheated length is equal to 0.332. Reynolds number raised to half. Prandtl number is how much? 0.703 raised to 1 by 3. What is this value? Okay. So just substitute this in this equation. Nu at x is equal to L with unheated length is 1 minus is epsilon by x is x, or here it is L. So it is 1 by 2 minus 1 by 2. It's 0.5 raised to 3 by 4 to 1 by 3. I think you can do this later, the mathematics part. So you will get around, please check whether the answer is coming close to this 185.27. Now it's simple, like hx is equal to k by X. Here x is equal to L. Okay, nu x that is equal to L, which is equal to 0.0282 by 2 into 185.27. So it will be close to 2.61 watt per meter square Kelvin. Okay, so this calculation you can do it later and check whether you are getting this answer or not. So if you want to read further about this unheated length, you can refer back to the Incropera textbook or any standard heat transfer textbook. So now, up to this point, we were discussing about the flow over a flat plate. Now we are going to the internal flow part. In this question, we have a water which is entering the pipe at a rate of say 0.01 kilogram per second and a temperature of 20 degrees Celsius. The pipe has a diameter of 50 mm and length 3 mm, is subjected to a wall heat flux of 2, 2500 x. So it's a function of x. The heat flux is a function of x. The bulk mean temperature of the water leaving the pipe. So you will try, or I should start solving this.
Sir, it is a problem of constant surface heat flux.
So I will start doing this. So in this pipe, we have a pipe flow. Okay. So with the mass flow rate is given 0.01 kilogram per second, and the temperature, inlet temperature is 20 degrees Celsius, and the diameter of the pipe is 0.05 meter, and length is 3 meters. The heat flux is a function of x. Okay. So I am taking a small elemental part of dx. So the heat it is getting is ux times the perimeter. Okay. So what is the surface area through which it is taking heat? That is perimeter times dx, right? I hope you understand how I wrote ux into p dx. Okay.
Yes, sir.
Yeah. So this is the heat that is coming to this elemental strip. So which is set temperature, uh, which is having a temperature change of dt. Okay. So if I am writing qx p dx is equal to m dot cp dt. Am I right?
Yes, sir.
Yeah. So now we just need to integrate this from 0 to L and Ti to T0. Can you please integrate? So just substitute these values. What is the perimeter? That is like integral 0 to L 2500 x. Perimeter is pi d. Okay. To m dot cp, it's like t o minus ti. So it will become 2500 into pi d into x square by 2 L to 0 m dot cp to minus ti. This is 2500 pi d L square by 2 is equal to m dot cp to minus ti. So now you got the solution because we are fast to find out t0, which is equal to 1250 pi t L square by m dot cp plus ti. Okay. Can you please substitute these values and say what is final answer?
62.8.
Yeah. So the answer is 240. So here it is just a simple energy balance there is that we have applied. Okay. Now we are going, I mean, it's the same question. The heat flux at the outlet is given, right? That is 500 watt per meter square. And the convection coefficient of the pipe outlet is also directly given. What is the surface temperature of the outlet? It's just a one single equation. So can you please say just a fundamental equation? That is Q is equal to HTS minus T infinity or TO, right? The surface. Okay. So here, what are the given things? Q is given, that is 500 watt per meter square. HS is all given, 100. TS is what we need to find out. Where is the TO? TO we get from the previous equation. Okay.
But sir, for that TI is required.
No, TI is not required. It's like this is the pipe, and here we have a heat flux. It's a convection from the surface to the bulk mean of the outlet, or the bulk mean temperature of the pipe. Here, but the problem is there is it's like the length is given. Okay, so the length is according to this question, it should be the heat flux at x is equal to 3 meter. In its outlet, it should be 7500. So you can check, you can calculate according to this. Because heat flux is given as a function of 2500 times x. Okay, so here the outlet we are having at x is equal to 3 meter. So the heat flux is 7500 watt per meter square, and the convection coefficient is 1000 watt per meter square. Then we can take the T out of that we have calculated from the previous question. Okay, so T out is equal to Q dot by H plus Ts. Q dot is 7500 by what is H? 1000 plus 62.8 is 7.5 plus 62.8. What is the answer?
80.3.
80 or
70.3.
70.3 degrees Celsius. Okay. So this is a question that it's like bulk mean temperature. So this was a gate question that was asked in the previous years. So we have a flow through a pipe of radius r. The velocity and temperature distributions are given. We are asked to find out the mixing cup temperature or the bulk mean temperature of the fluid. So what is the value of bulk mean temperature? Tm is equal to 2 um r square integral 0 to r u rx t rx r dr. This expression is already derived by the professor in the lectures, so you can look back to the how this is derived. Okay, we know the temperature profile is not linear across the cross section. So in order to make our we should have an average, means everything we are to measure is the average quantities. So this is the average temperature over any cross section of the pipe. So now it's just a mathematics part only. You just substitute it into this expression, just integrate it and give me the answer. So I will wait. We got the answer. Okay, so Tm is equal to 2 by u means
Excuse me, sir. Actually, this I have got the answer, but that in every option C1 is missing. I don't know
C1.
why. C1 is missing.
There is no need of C1. You will not get C1 at the final answer. That's why it's not there.
But I am getting, sir.
Okay, I will solve. Please check whether you have got the wrong.
Okay,
So
sir.
2 by r square integral 0 to r. So u rx, it's a constant function c1, c2, 1 minus r by r the whole cube, r dr. Okay. So c1, c2 I'm taking common because it is constant, r square. Then this I am breaking integral 0 to r, 1 minus r cube divided by small r cube, r dr. Okay. So if we integrate it to c1, c2 divided by r square, this is r minus r raised to 4 divided by r cube, 0 to r dr. Okay. 2c1, c2 divided by r square, r square by 2 minus r raised to 5 by 5. I'm putting the limits. Okay. So I'm skipping one step. So I integrated and substituted the limits as r. Okay, yeah, fine. So it becomes 2c1 c2 divided by r square. This is 5
No, no.
3.
So in this second term, there should be in denominator R the cube also. Second term.
Which one?
R5
This is r
divided
square.
by. No, 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 no. This is correct. R5.
No, it's not correct because it is r raised to 5 by r cube. So when I put limits, it is r5 by r cube. It becomes r square.
Okay. Yes, no problem. Yeah, it is R square is okay.
Hmm.
Yeah.
So it becomes 10. Okay. R square got cancels. It will become 3c1 c2 divided by 5 Okay. So you will get this answer. But the gate question,
So C1 is missing.
C1 is there. But you
Yeah.
have to you have to do one more because you check whether this is matching the answer. No. But in two answers, there is no at all. You can find the mean velocity also. Okay. This is how gauge questions are framed. I hope you understand. In two options, there is no at all. And your answer with is not matching with any of A or D. And
Yes, sir.
C1 is also not present. So which means you have to do some more simplification. What is
Okay.
Okay, 2 by r square 0 to r c1 c1 r dr. Okay, 2 by r square c1 r square by 2. So is equal to c1. So if you substitute this in that value tm, which is equal to 3c1 c2 divided by 5 So 3c1 c2 divided by 5 c1 is 0.6 c2. Okay, I hope it is clear now. Is this question clear?
Yes, sir. Means we have to calculate once more the UM
Yeah,
because we are not getting the correct option with C1.
yeah,
So we will be putting the value of UM, and for that we will be calculating the mean velocity,
yeah.
and then we will be putting value of UM in the expression we have already got for with the integration.
Yes, right.
Yeah. Okay. Okay, sir.
Yeah. Okay, I hope so. Today we will stop here. I hope the questions was are you have you solved this kind of questions earlier, or it's the first time you are getting this kind of questions?
No, sir. I'm getting first time.
So as I said, this is a gate question. Like uh, it was solved. I don't remember the which year it is asked. So then while doing gate question, you should give consideration to the option also, because if this question was asked in a like normal examination, even if you write this expression 3c1 c2 by 5, you may get some answer, or it is you can say it's right. But in gate or in objective examination, you have to choose from whatever given, that is a b c d. Okay. So you have to modify your answer such a way that it matches with the option. So that is very important in competitive exam. And okay. So I hope this session was helpful for you. I hope. I think it's
Yes,
almost
sir.
six weeks, so I need to get a feedback. I hope this was helpful for you in
Yeah.
solving some of the
Yes,
questions.
sir. Yes, sir.
Yeah. So okay, then we will wind up this session here, and thank you for joining, and have a nice week ahead. So see you in the next Monday, the same timing. So thank you very much.
Okay, sir.
Thank you.